Hello and welcome to Batty.com. We are starting a series on the importance of testing, and to kick it off today, we are presenting the Batty.com 90 through 96 Corvette Instrument Panel Tester. Rumor is that Crazy Uncle Burton went for a late night stroll one evening around his development basement lair and tripped over a pile of old Motor Trend magazines that he thought he threw out after they canceled his favorite shows, Roadkill and Hot Rod Garage. He whacked his head really hard on the concrete, and this is what gave him the idea for the computer-controlled dynamic sensor network. Afterward, he spent thousands of hours in the development department basement cave lair inventing this instrument panel tester. The question comes up over and over again, do you actually test repairs before you send them back? Yes, we do. We all know from eBay that if it isn't tested, it doesn't work. So our repair philosophy is if it's not tested, it's not repaired. We test everything for 24 hours before we ship it back. Here's how we do that. We have spent the last 3 years developing the Batty.com 90 through 96 Corvette cluster tester. We are quite proud that this is a product that we developed right here at Batty.com. Any cluster you send us will be tested using this process. And as of 2025, there's no charge for those tests. There are many variants of the instrument panel used in 90 through 96 Corvettes. And this tester is designed to test each and every feature of every style cluster. This is not simply a gimmick box full of switches and wires like some of the testers out there. This is a fully computerized instrument panel tester with a color screen and touchscreen input. It is designed to simulate all the sensors and all the computers in the car that the instrument panel would interact with. The computer inside controls the dynamic sensor network, which lets the tester test every function of the 90 through 96 Corvette instrument panel. This includes the LCD panel, the panel lighting, the panel dimming, and it tests every function of each analog gauge at each of its marked positions. On the back, you'll find a cooling fan to evacuate the heat generated by the dynamic sensor network. There's also a ground lug on the back to make it easy to connect the tester ground to the ground of any test equipment that you're using. Everything is powered by a medical-grade power supply. And one of the problems we discovered early in testing was that after a few thousand uses, the test cable wears out, so we made that test cable replaceable. This is a 94 through 95 ZR1 cluster, or a 96 LT4 cluster. We know this because of the white gauge faces, which started appearing in 1994, and we know that it has an 8K TAC. When we fire up the tester, we see a little advertisement for Batty.com. We also see a QR code that will take you to our website for repair information and parts. And then it's going to ask us for the year of the cluster. This tells the instrument panel what signals and senders to connect to the instrument panel. This is a 92 through 96, and we'll say next. And we'll change the TAC setting to 8,000 RPM maximum. Next, we have the option to run in a burn-in mode or to run individual tests. The burn-in mode is what we'd use after a repair to test the cluster in an unattended fashion. We'll show you that a bit later. Now we'll choose next to proceed with the guided test. We notice the instrument panel behaves differently when it's warm than it does when it's cool, so we are showing you the initial test conditions. This next screen is called Quick Test. It shows us an image on the LCD screen, and it sets all of the sensors to nominal operating conditions, and it sets the TAC to full scale. Mileage is not stored in the cluster, so we made up something that the customer would know is not supposed to be their mileage, and we chose the name of our company. There's a problem with this instrument panel. It's being commanded to show 8,000 RPM, and we see that it's showing much higher than that, so we'll make a note to fix that while it's apart for the other repairs. Oil pressure, oil temp, water temp are all set to the larger marked positions. The speed and fuel level you see on the screen is not measured by the instrument panel. This is the job of the CCM. So we made up a 60 mile an hour and full gas tank for the purposes of this screen. The next test is the all LCD segments on test. What we're checking is to see if all segments on the LCD can be turned on, including the really small decimal points. Can we turn off all the segments? We're also checking the contrast of that information. And what that means is, are the segments black or have they started to fade to a lighter gray? The next test is the TAC test. We're sending specific values of TAC signal to the cluster, and then we're checking to see if the indicated position matches the position of the sender. Since we see the tach reading slightly below 0 RPM, we know there's likely a problem with the tach analog calibration IC. 4,000 RPM input gives us about 4,400 indicated, and 8,000 RPM reads about 1,000 RPM high. So again, we think we have a problem with the analog calibration IC. Next test is the varying tach test, and it's going to step through individual 1,000 RPM markings on the tach face. 1,000, 2,000, 3,000. This lets us test it at idle, at full RPM, and everywhere in between. We're also watching the movement between steps to see if that needle moves freely, or if it's maybe dragging against the gauge face. The needle is moving freely here. Another part of the varying tach test is that at any point in time, we can stop it to let us take photos and test the tach circuitry at a specific RPM. This lets us calibrate the tach. The next step is to warm up the analog gauges. They respond much differently when they are warm than they do when they're cold. So we want to make sure that they're warm like they would be when they're operating in your car. And it takes about 90 seconds to warm those gauges and coils and shunt resistors up for a proper test. Next, we are stepping through the oil pressure positions. We compare the number on the tester to the number on the display to see if they match. This one does appear to match, but it's moving a little bit slowly. So we'll clean it up during the rebuild process. This is the oil temp test. We're doing the same thing here, comparing marked positions to the expected value on the tester. This one is working properly, and this one is moving freely the way it should. Next test is the coolant temperature. This one's working properly as well. The next step is moving the gauges between all of their known positions. It's a way to check the movement of those needles. We're going to move them from 0 scale to full scale and back again. This next test is a voltage gauge test. The instrument panel measures the input voltage and presents it on screen. We are indeed testing at 15 volts. This is a more realistic test than 12 volts would be. It simulates the expected output of a good alternator. Next, we check to see if the indicated reading matches the on-screen value. The marked position near that gauge would be 15.5, so we are indeed reading what it should. The next test is running all lights at full brightness. This lets us see how bright it should be when it's in full sunlight with the headlights off. It's prompting us to turn the cluster over and look at the back, so we'll do that now. What we see is that the bulbs are all lit, and they're all lit about the same brightness. This would show us if we have any bulbs out, or if we have any bulbs that are running at diminished brightness, which is common at the end of a bulb's life. The next test we see is running the lights at 10% brightness. This simulates the dimmer switch function, either with the headlights on or when we're operating with the headlights off and in a dark condition, like testing in the garage, driving through a tunnel, operating at dusk. The LCD panel and the needle illumination bulbs and the gauge face bulbs dim during this test, but the warning lights around the edge always run at full brightness the way they would in your car. This completes the testing process. The next screen shows us the final voltage and temperature for our reference, and then a splash screen tells us where we can get parts, and it says this was made by Crazy Uncle Burton, and then it shows us the firmware of the tester. The next screen gives us a chance to reset the test for the next cluster. Burn-in mode is how we test the cluster when we finish the repair. It runs in an unattended fashion and tests each of the functions of the cluster. It tests each function of the cluster hundreds of times over the course of 24 hours. Here we see it stepping through all the tests we showed you previously. This helps us identify infant mortality issues with light bulbs, as well as heat-related issues and cold solder joints. When the 24-hour test is done, we do one final inspection test to be sure everything is working the way it should, and we ship it back to the customer. People who install the tach IC themselves frequently ask us how we calibrate the tach here in the repair shop. Here you see a photo of that setup. The cluster tester comes with this extension cable, which inserts between the tach needle movement and the circuit board. This gets us the space we need to adjust the potentiometer. Then the cluster tester drives the tach circuitry at half scale and full scale, and we manually adjust the analog calibration IC potentiometer until the needle matches the input speed from the cluster tester. Another question we get frequently is, why is it so expensive? We spent about 3 years developing this product. This is major version 6, and there have been countless prototypes along the way. So the development costs are high. It's manufactured in fairly low volume, so economy of scale is out the window. As a result, it's mostly used for our in-house testing of the clusters we repair. If you or your car club want one, they're still available on the website as of July 2025. When you purchase a cluster tester, you get the 15-grade medical power supply, you get a TAC extension cable, and you get a USB drive that contains a repository of all the info we've compiled about 90 through 96 Corvette clusters. This includes schematics, wiring diagrams, year-to-year variances, expected sensor values, a collection of high-res images of the expected cluster reaction for each and every style cluster, for each and every step in the test. We are currently working on more videos to showcase the importance we place on testing here at Bati.com. If you want to see more of that kind of content, go ahead and like and subscribe below. As always, you can go to Bati.com to find the parts and tools used in these repairs. You can find more information about us in the bio below, and we have even more info like free schematics and wiring diagrams available on our website, Bati.com. That's BATEE.com. Thank you so much for supporting us. My name is Brian Thompson. On behalf of Tristan and Beverly and Crazy Uncle Burton, thank you for watching.